So now we would like to run the simulation, and it should be good to go from what we did in the last lecture. So you can hit run, and it's going to start to run a transient simulation of the flow over this airfoil. If we take a look, here I've inserted a gold plot. You can do that yourself by going insert, oh, not the table. You want to insert a goal plot, select both of the goals, and here you can see that it is transient. Oh, actually, let's right-click that, and let's change the x-axis to physical time. And so you can see that, actually, we can also change, let's go from minus 0.2 newtons, 0.02, to 0.1 newtons. And you can see that we have a very steady simulation. It's very low amount of force because we have such a slow flow, and there it ran our 10 seconds, and there's virtually no change throughout that entire time, which makes sense. We should be well within the laminar range. But we see solver is finished, so we're going to exit out, and we're going to start to look through these results. First thing we'll do is insert a mesh to see what SolidWorks has done with the mesh. Go ahead and select XY plane and OK. And we want to hit display and uncheck lighting as usual. And you can see, okay, well, it's not really refined around the airfoil at all in this case because we haven't done much custom with the mesh, but we have a reasonably small mesh. It is refined very slightly. The elements on the outside are slightly larger than the elements around this curvature, which is what you would want to do in order to ensure a good quality result. And now you can hide that and insert a cut plot. And the first cut plot we're going to look at is velocity. So let's set this to the x direction velocity, and let's set the number of contour levels to 30. And as you do that, you can see that we have a bit of an asymmetrical profile over the airfoil. So we've got, which makes sense because we have a flow that should be pointed upwards 5 degrees. And so, it's not a huge asymmetry if you look at this, but you see we have very fast flow over the top of the wing. And we've got slow flow right at the front where the air is butting up against the airfoil. We also have some slow flow and a bit of a wake forming at the reverse of the airfoil. But it doesn't look like we have anything below zero. So we have no reverse of the flow field. We've got no circulation or anything like that. And this behavior is what we would expect to see if we're generating some lift, because we've got fast flow over the top, and so hopefully the pressure is a little bit lower there than at the bottom, and we have this nice asymmetric profile. And actually, one thing to note is that the velocity field is affected even before the airfoil. So in steady state, that little entrance effect at the beginning of the simulation, and the reason why it's not just steady right away, is because you have to have the buildup of pressure against the airfoil to begin with. And you're going to notice that it will affect the flow field even before the air ever touches the airfoil. So if I have flow coming towards an object and I introduce a disturbance, that affects the flow field before the object. There's a propagation of that effect outwards in front of it, which is interesting to note. Some people sort of mistakenly believe that the flow field is only going to be affected going behind the object, but here you can see that that's not the case. So actually, we don't even have to hide that. Let's just insert on top of that a new cut plot, and let's look at the I want streamlines. Here we go, streamlines. And then uncheck contours. And you can accept it like this for now. You can play around with the streamlines. But here you see, okay, we have no separation, very well behaved streamlines over the whole object, which is what we like to see. And you can see the effects that we discussed in class. We have this downward curvature. And so that should correspond to, hopefully, a region of low pressure, right? Because as you go far out, pressure is going to be atmospheric. As you go far down, pressure is going to be atmospheric. And so that means that in order to keep the fluid hugging the airfoil, you're going to need a large amount of pressure on the bottom of the airfoil, pushing that curved line down, as well as a low amount of pressure right on the top of the airfoil, so that the atmospheric pressure is sufficient to bend the airfoil, bend the flow around the airfoil. And let's hide these first two cut plots. And then let's insert another cut plot which shows pressure. That should be good. Actually, pressure will not tell us much with this yet because we're looking at this too slowly. So we'll keep it, just keep in mind that that is something we will do. And then the next thing, as we speed up the flow, the next thing we're going to do is we're going to insert goal plots. And so select that you would like both of those with physical time. You can show them. You can export them to Excel. And you can accept that. And for the goal plots, you'll notice that if you zoom in, so let's enable editing. Okay, here it's easy to see. So the lift force, essentially, you're seeing small disturbances, but they're very minimal, right? So there's a moderate amount of unsteadiness in this flow field, but nothing major, and it's not really affecting the results very much. And we don't observe any substantial asymmetries in the results that we were looking at. So what we'd like to do now is ask ourselves, okay, what happens as we speed this up? So let's hit general settings, and then let's go to initial and ambient conditions. And for velocity in the X direction and the Y direction, I want you to increase them by a factor of 100. And in your participation assignment, you're going to be asked to compute the Reynolds number for all of these conditions. And so clearly, in this case, since we're not changing the fluid or the geometry, this is going to correspond to increasing the Reynolds number by a factor of 100. Oops, one too many times, had a delay there. So with that, you can click OK. And then we're going to want to refine the mesh. So let's edit this mesh and set the refinement level, the global refinement level, to 5. Ensure that nothing else is checked here. You can accept it. And then we want to rerun. And when you hit run, it's important to make sure that we're doing a new calculation. But sometimes it doesn't default to that. Oh, this time. So the reason why it's doing this now, this is a problem in some people's assignments, is if you run it without ensuring that you're making a new calculation, it might just use your old mesh or old settings. In this case, since we've changed general settings, we don't have to worry about that. It's just automatically giving us the right setting for run. And so this will take slightly longer. We can insert that goal plot again. So select both of the forces. And in this case, X and Y aren't exactly equal to lift and drag because we have the flow entering at an angle of 5 degrees. So let's do the same thing we did last time, where we set this to minus 0.2. Set this to 0.1. This should be 0.02. And then we want to set the x-axis to physical time. So now you can see some unsteadiness. So the drag is still pretty low on this, but the lift is substantial, and it is not constant in time. It's definitely changing as we advance in our simulation. And so that tells you that there is transient behavior in the flow field. And if you recall, and so actually now we're starting to see a waveform develop. And so this is quite reminiscent of what we saw in our flow separation in wakes. And so that should be tipping you off that perhaps some of the behavior we saw for flow separation in wakes we'll see here. And you can think that, as you increase your angle of attack to a sufficient degree, your airfoil, even though it's a streamlined body from one direction, it's definitely not a streamlined body from the other direction. And so if you have sufficiently fast flow, you are going to form a wake, and that wake will have unsteady flow features in it, as we will discover. So we'll just give it another moment here to approach completion. Full 10 seconds. Almost there. So you see some of the same unsteadiness in the drag force as well. And that's because all of these forces are co-determined, right? So the unsteady behavior is causing time-varying flow fields, and the speed of the flow is going to determine the amount of friction that you feel over the surface. So there's a very coupled forces. All right, so it looks like we're done. We can exit out of this. And we're going to go back to the mesh and take a look. And so now you see we have much more refinement around this airfoil, which is great. It's going to be necessary for analyzing these higher speed flows. And the first thing we want to see is the velocity. And now, very unsteady. So everything we were seeing from that force is confirmed when we look at the velocity field. And here, if you look at the x-axis, we have some seriously negative velocities relative to the maximum velocity. And so that indicates that you've got a recirculation zone. And we have flow separation. And then we have unsteady vortex shedding behind the airfoil. So as we sped up with that angle of attack and this profile, this shape of the airfoil, which has quite a blunt bottom and not a lot of curvature along the bottom of this airfoil. It's quite flat. And so that is inducing separation as we increase the angle of attack. And again, you do still see very fast flow over the top, but we're going to have a pressure gradient going in the other direction. That's what's indicated by this behavior. Well, you'll always have that pressure gradient, but here it's high enough to induce flow reversal. And now we can show the streamlines, and those reveal, as we expected, there's a recirculation zone here. And that tells you that you have a lot of viscous forces in that region as well, right? Because as we discussed in the lecture, you're going to have a rotational behavior in this region. If you look at a fluid element, it's going to be rotating, and you can't have that with inviscid flow. So somehow the viscous forces in the air are sufficient in this region to see circulation. And now is where we will benefit from looking at that pressure plot. Or will it, actually, I'm not 100%. Yeah, okay. So now we're starting to see, and look at how slight this is. So you don't have a very high pressure gradient, but we do observe a pressure gradient. And this is quite characteristic of the pressure field that you get over an airfoil, where we have low pressure at the front and high pressure at the top. And so whether or not we're generating lift, you're always going to have, quite a bit, it's often marginal. So if you integrate the pressure over the top and the pressure over the bottom, those forces are often going to be quite close. So it's like you're just having the balance might tip from negative to positive, but the overall pressures are substantial. And the high pressure region at the bottom, it's not distributed throughout the whole bottom of the airfoil, really. Like, you're quite close to atmospheric for a lot of this. And given the shape of this profile, we actually have kind of a low pressure region at the bottom of the profile as well. But you have a very high pressure spike at the front where the air is building up pressure as it butts against the airfoil. And then we have this region where we have quite a low pressure on top. And so that's in principle where the drag comes from. But then we have an adverse pressure gradient as the pressure goes back up when you curve around the airfoil. And so in this case, that was sufficient to induce separation. And what we want to do next is we want to increase yet again. And so we're going to go up to a velocity of 60. So we went from 0.01 to 1 meter per second, and now we want to go up another factor of 60. So 6,000 times higher than that initial velocity. So go to your initial conditions, and then let's type in 60 here. We won't need, so let's go 59.772. That's in the X direction. And then let's get the sign of that. 5.229. Okay. The grid should be fine for this, so we're going to rerun it. But actually, sorry, I do want to change one of those settings. So close. Let's not run this. We want to go into the solver, and you want to set the physical time to 0.2 seconds. And that's because the flow is going so much faster that it's going to reach a steady state very quickly. We don't have to worry about the amount of, so let's just go mesh, new calculation, make sure we've selected those and run. We don't need the full 10 seconds to get the steady state behavior. What's going on there? So let's open up the solver. And as we do that, you might have enough time to insert a goal plot, but maybe not. It's going quite quickly. So you can see there, we have unsteadiness at the beginning, and then we very quickly level off. All right. And you can close the solver. And we've seen this mesh already. The first thing we want to look at is the velocity field. Okay, so now we have very fast flow. And you can see that the asymmetry is much less, and shouldn't say the asymmetry is less, because there's definitely still an asymmetry associated with lift going on here, but you're seeing that you don't have these large sort of gentle wakes. You have much more extreme flow over the surface. This is actually the fastest flow that we've considered in the course so far, and we have 84 meters per second on the top of the wing, which is actually quite fast. Let's look at the streamlines now. And so this is interesting. The streamlines are very well behaved. So what is going on? We increased the speed from before, and so we kind of expected more extreme flow behavior. But what I indicated would be important early on in this lecture is that we also selected laminar and turbulent. So this is giving us the ability to have laminar, turbulent, transition from laminar to turbulent. Those effects are all being considered. And what we did is we increased enough to get a turbulent flow field here. And what that means is that we're entraining momentum into the boundary layer, and it's enough to overcome that adverse gradient and ensure that we have no separation and we have very smooth velocity profiles leaving the trailing edge. In this case, that is going to reduce the pressure drag on this wing. And we can hide these cut plots. And so we don't have unsteadiness either. We can insert that velocity cut plot, and here we have a very beautiful velocity field, very high concentration again at the front, and now we have a higher pressure all throughout the bottom. So you can see this is a much more effective lift scenario. You can hide that. You can also insert a cut plot of vorticity. And so with the other flow, if you insert a cut plot of vorticity for that slower flow field, you'll notice that there's going to be a lot of vorticity at the back where we have rotational flow. Here, that phenomena has gone away because we have maintained our boundary layer attachment to this flow profile. And what I'd like to do is insert one more cut plot. And to do this, we're going to add a parameter. I believe we'll need to do that. And then under turbulence, you want to select turbulent energy. And then you'll need to go back to contours, find turbulent energy, click OK. And so this is how you can tell that you have a turbulent flow. And what that's doing is it's quantifying the amount of fluctuations essentially in the flow. So when you have turbulent flow, you have very rapid changes in the velocity. And if you look at the difference between the mean velocity and the instantaneous velocity, that's a fluctuation. It's an instantaneous change in velocity. And this is like an average fluctuation in some sense. That's what we're getting when we look at this flow. And if you plot this for the first case, for instance, you'll see totally nothing. There's no turbulent energy in that flow, or for the second. Actually, the way the metrics counted any sort of unsteadiness, it might count as a turbulent energy, but it shouldn't. But it might. It depends on how it's calculating it. But in this case, this is really due to actual turbulent behavior. And so with that, we've kind of explored how changing the magnitude of velocity and transitioning from very slow laminar, almost akin to creep flow, to a faster laminar gave us separation. Going then to turbulent allowed us to train additional momentum in the boundary layer and ensure that we were, that boundary layer remained attached. And so we saw different behaviors of this profile. What we want to do in the future is look at different profiles and how do those behave for different angles of attack and different flow speeds, and then also maybe investigate a little bit how we can design these airfoils ourselves. So that's all for this lecture.